Well, good morning. Today we are going to start our second day of looking at the process of writing formulas and the names for salts. Last time in class, when I was still with you, we learned how to write the chemical formulas for what we call the simple salts. What we're going to do today is take the skills that you learned last time and we're going to extend them into writing the formulas for what we call complex salts. And then we're going to take these complex salts and use them as the opportunity to start writing, flipping this process and writing the names based upon the formulas, where up until now we've just written formulas for names. In order for you to be ready for today, you are going to first of all need to gather note-taking materials. Would strongly encourage you to be taking notes in pencil. There will be a little bit of erasing that you'll need to be doing today. So a pencil would probably serve you better. And so grab note-taking materials. In addition to that, you're also going to need your periodic table. And then finally, you need to get the yellow ion chart that you received from me last time in class. And if you weren't here, please ask for one and we'd be happy to get you one. So take a second, gather together your note-taking materials, periodic table, and your yellow ion chart. Now that you've had the opportunity to gather these materials together, what we're going to do is let's take a look back at the homework that we solved last time, the homework that we did last time, and use that as the basis for what we're going to learn today. So if you look back at the chemical formulas that you wrote for the salts that we looked at last time, you'll notice that these things have several things in common. First of all, the way that they're written, they are always written positive ion first. And you may remember from what we talked about last time, the positive ion will be the metal. That's the electron loser. It's the element that's on the left-hand side of the periodic table. And so the metal is always written first. Then, of course, the nonmetal will be written second. That is the electron gainer. The nonmetals are small and strong. They take in electrons, and those form the negative ions. So we always write the formulas for salts, positive ion first, negative ion second. And then remember that the way that we write these is so that the positive and negative charges balance. And the way that we do that is by adding subscripts to get just the right number of positive and negative ions so that they first meet, creating what we call a salt, but salts have neutral charges. The positives and the negatives balance, and so when we write the chemical formulas, we do it in such a way that the positives and negatives do balance, and that's what the subscripts are for. So these are the things that we talked about and learned last time. What we're going to do today is we're actually going to take this very same process, the same logic, all the things that you should be now comfortable with, and what we're going to do is we're going to invite into the conversation another class of ion. And interestingly, you've seen this before, you just didn't know it. Let me show you what I'm talking about. Let me introduce you to this new type of ion. Again, as you see on the screen, up until now, our ions have simply been atoms. Copper, for example, and chlorine, and aluminum, and oxygen, and nickel, and bromine. So up until now, our ions have simply been elements. Well, it turns out there is a whole nother type of ion that exists, and they also form salts, and we're going to talk about those for the rest of the day. These ions are what are called polyatomic ions. This, of course, should be something in your notes. Polyatomic ions are simply molecules with a charge. And if you think about the name polyatomic, I think you can see why these are actually molecules with a charge. So poly means many. Atomic, of course, refers to atoms. So what we're talking about are many atoms, so groups of atoms bonded together, and these are what we would then understand to be molecules, but these molecules act as ions. So what we're talking about are ions or molecules that have a charge, polyatomic ions. And some of you may be thinking to yourself, wait a second, we've seen these before. And a matter of fact, you have. You may remember from several units ago, and even the previous unit, when we draw the Lewis dot structures for molecules with a charge, ions, we put them in brackets. And so this is actually a page right out of your previous homework, a homework assignment from a previous unit. And you'll notice that all of these molecules, all covalently bonded, all of these molecules have a charge. So this is the molecule OH. This is the molecule OH with a charge of -1. This is NO2 with a charge of -1. This is PO4 with a charge of -3. And then this is C2O4 with a charge of -2. So these are all polyatomic ions, molecules with a charge. Now guys, here's the nice part. You don't have to memorize these. You do need to know them, but you don't need to memorize them. That's where this yellow sheet comes in. So if you grab the yellow sheet and look at it with me, you'll notice that this yellow sheet is a chart of polyatomic ions. You'll notice, first of all, that it's broken into cells. Across the top, in the top two cells, you'll notice that you've got ions with a +1 charge. We write it 1+, but it's a +1 charge. So ammonium, which is NH4, has a charge of +1, and then off to the right, we have mercury 1 and mercury 2. And both of those have a charge of +2. So you'll notice that these are grouped together by charge. Down below we have the polyatomics that have negative charges. And you'll notice that in this entire table you're given 3 bits of information. They're grouped together by charge, then you've got their name, and then you've got their chemical formulas. And so if you allow your eye to scan down the bottom of this chart, you may notice that the 4 molecules that are up on the board in front of you are also on this yellow chart. So let's see if we can find them. So starting with OH, if you allow your eye to scan down the left-hand column down at the bottom, you'll notice that, as it says on the board, OH has a charge of -1 or 1 negative. Those are the same. And then you'll notice, guys, that OH is about 2/3 of the way down, and the name of this polyatomic ion is actually hydroxide. So OH with a -1 charge is hydroxide. So then continuing to this next one, you'll notice that this also has a -1 charge. So you'll find it in that bottom left-hand area. And this is NO2. So if you allow your eye to scan almost to the bottom of that group, you'll notice that there are 2 polyatomics that both contain nitrogen and oxygen. Be careful, NO3 is nitrate, but the one that we're looking at here is NO2, and that is what is called nitrite. If you're curious, the 8 and ite endings actually indicate how many oxygens there are. So 8 always contains more oxygen, and ite is less oxygen. Doesn't mean 3 and 2. 8 just means more, and ite means less. So continuing down again, the next polyatomic that we've got is PO4, but you'll notice this has a -3 charge. So that puts us in the far right-hand column, and this molecule, this polyatomic ion, is actually PO4 with a -3 charge, which is phosphate. And then finally, the last one that we have on the screen, this guy has a -2 charge. So we look in that center column, and this is C2O4. And as you allow your eye to scan down that column, you'll notice that C2O4 actually is given the name oxalate. So again, you won't need to memorize any of these, but you will need to be able to navigate this chart, as we are now going to use these ions and use them to write chemical formulas for salts. These are what are called complex salts because they contain more complex polyatomic ions. So now we understand what polyatomic ions are. Now let's talk about how to identify them. And guys, if you turn your attention back to the yellow chart, you'll notice that if you read the names of these ions, most of them begin with ate or ite. Now remember last time in class you learned that when you're naming salts, you change the name of the second ion to ide, like sodium chloride. Well, you'll notice that on the polyatomic ion chart, most of these end in ate or ite. So if you have a salt and its name ends in ate or ite, that's going to be a polyatomic. If it ends in ide, like sodium chloride, that would be an element. But realize there are 3 exceptions. Those exceptions are hydroxide, cyanide, and peroxide. Why don't you take a second and on your polyatomic ion chart, find those 3 ions and underline them. So first of all, hydroxide. Again, we already found that in the -1 column about 2/3 of the way down. Then cyanide is actually directly above it. It's carbon and nitrogen bonded together. And then peroxide is actually in the center column about 5 down, and that is an O2 molecule with a -2 charge. So these are the polyatomics that end in ide. They are the 3 exceptions, and you just need to remember that when you're trying to find hydroxide, cyanide, or peroxide, these will not be elements. They'll be on the polyatomic ion chart. When we are writing the formulas for these complex salts with these polyatomics in them, it's the same game that you learned last time. Nothing changes. We're still writing formulas, we're still balancing charges. The positive ion goes first, the negative ion goes second. None of that changes. There is one thing though that is a little bit different. So we write their charges, we balance their charges just like before when we're writing formulas. The only thing we have to keep track of is this. If you need more than one of a polyatomic ion, you need to put it in parentheses. Again, don't scratch this in your notes. You're okay without it, but just keep this in mind. And I'll show you an example or two in a minute, but understand that if you need more than one of a polyatomic, it must be in parentheses. But conversely, if you only need one of a polyatomic, putting it in parentheses is actually incorrect. So really the only new thing that you need to keep track of here is how to deal with parentheses. So with that in mind, let's look at a couple examples. So why don't you write these down with me in your notes. So skip down about 3 or 4 lines and off to the left, let's look at this salt called calcium sulfite. Now again, this is exactly like writing the formulas for the simple salts. The first thing that we need to know is the abbreviation of the ions. So switching colors here, calcium is big C, little a, and that does matter. And then we need to figure out what sulfite is. But guys, you'll notice that it doesn't end in IDE. It is not sulfur. Sulfite is polyatomic. And so if you look in the center column, 4 from the bottom, you will see that sulfite is SO3. So it's a sulfur bonded to 3 oxygens. So now what we need to do is we need to find their charges. So looking at calcium, which is element number 20 on the periodic table, you'll notice that its charge is +2. And then looking on the polyatomic ion chart, you'll see that sulfite is -2. So now we have their formulas and their charges, and just like last time, we just need to make them balance. So +2 and -2 first meet up at 2. What that means is we only need one of each ion. So when we bring these together to write the formula, we need 1 calcium, we need 1 sulfite, and that would be the chemical formula for calcium sulfite. 1 calcium and then sulfite, which is SO3, and we need 1 of those. And so this chemical formula then for calcium sulfite is CaSO3. Let's take a look at another example. Now we're going to try magnesium nitrate. Yep, nitrate. So to do this again, we need to look up their chemical formulas and their charges. Magnesium, element number 12 on your periodic table, is Mg. And let's just get the charge while we're there. It has a charge of +2. Now we need to know what nitrate is. And notice it's not nitride. It is not nitrogen. It's nitrate, ends in 8. And we find that in the -1 column near the bottom. Nitrate is NO3, and its charge is -1. Now we have to balance charges. Magnesium is +2, nitrate is -1. So the first place that +2 and -1 meet is at ±2. This means that we need 1 magnesium in order to have a charge of +2. Now, how many nitrates do we need? Well, the trick is each one of these nitrates, each one of these NO3s has a charge of -1. So if we need a charge of -2, that means we need 2 of them. So what we do then is we take our NO3, and this is 1 NO3. If we need 2 NO3s, which we do, we put it in parentheses and subscript a 2, meaning that we have 2 of the NO3s. So this then would be magnesium nitrate. Let's look at 2 more examples. So looking down at the bottom, now just like before, we have a positive ion that can have more than 1 charge. In this case, it's nickel, and nickel is element 28. And looking at the periodic table, that can either be +2 or +3. But the Roman numeral, in this case 3, tells us that we use the +3 charge. So nickel, big N, little I, has a charge of +3. Now we need to find hydroxide, and this ends in IDE. So our first thought might be that this is an element. So what element would have its name turned into hydroxide? Well, there is no element called hydroxium. It's not hydrogen, because that would be hydride. It's not oxygen, because that would be oxide. But then we remember, oh, this is one of those 3 polyatomics that ends in IDE. We've already underlined it on our table. And hydroxide, as we see, is OH with a -1 charge. Now again, we need to balance charges, so we've got +3 and -1, and those meet up at ± -3. This means then that we need 1 nickel, and we need 3 hydroxides. So 1 nickel would simply be Ni. Now if we need 3 hydroxides, we go O, and we go H, and we go 3. And in writing that down, I'll bet you see the problem. The problem is if we write it like this, that only gives us 1 oxygen and 3 hydrogens. And we don't want 1 oxygen and 3 hydrogens. We want 3 of the entire OH. And so as a result, this entire thing needs to be in parentheses. And now we have 3 of not just the hydrogen, but the entire hydroxide ion. Notice, guys, if that makes sense, that if we come back up to calcium sulfate, we did not put sulfate in parentheses. The reason we didn't put the sulfate in parentheses is because we only need 1 sulfate, and putting that in parentheses is unnecessary and therefore wrong. So let's get rid of that. All right, let's do one more example. So now we're ready to look down here in the lower right-hand corner at the salt ammonium phosphate. This one could be a little frustrating. The reason is because the positive ion is ammonium. And when you look for ammonium, you spend time looking for it on the periodic table, and you find out ammonium is not an element. Ammonium is actually on your yellow polyatomic ion chart in the upper left-hand corner. Ammonium is one of the few positive polyatomics that we're going to talk about, and ammonium is NH4 with a +1 charge. Now phosphate ends in 8. That tells us it's on the polyatomic chart as well. It's on the far right-hand side, being the only polyatomic with a -3 charge there. So now we need to make these balanced. +1 and -3 will meet up at ±3. This means that we need 3 ammoniums to have a charge of +3. So we've got NH4, but now if we need 3 of them, we need to put that in parentheses and add the 3. Now we need 1 phosphate. phosphate is PO4. So what we just wrote on the board represents one phosphate. If we needed more, we would put it in parentheses. But because we only need one phosphate, we do not put that in parentheses, and this then would be ammonium phosphate. So there you have it. This is the process of writing chemical formulas for complex salts from the names. Now what we're going to do is we're going to change the game a little bit. Up until now, last time and this morning, we've talked about how to write formulas given the names. Not surprisingly, we can also go in the other direction. We can take we can take formulas and we can write the names. And this is also an important skill to have. So let's talk about how we're going to approach this. So we're now going to talk about how do you write the names for salts. So guys, when we are naming salts, the first thing that we have to do, and you really need to get this in your notes, the first thing that we've got to do is we've got to determine if the cation can have more than one charge. And guys, I'm going to tell you right now, some of you are going to skip or just ignore this, and it's going to get you in trouble. You have to do this first. So when you're writing the names for salts, the very first thing that you've got to do is look up the positive ion, the first ion, the cation. Look that thing up on the periodic table and determine if it can have more than one charge. Now the answer is going to be yes or no. Either it can have more than one charge, and you'll see multiple charges on the periodic table, or perhaps it can't have one charge and it'll only have one number given. So for example, if you look at sodium, element number 11, it can only be +1. But if you look at copper, element 29, you'll notice that it can have more than one charge, in this case 2 or 1. So that's the first thing you got to do is figure out, can it have one charge or more than one charge? Now why do we care? Well, we learned about that last time. Remember that we use Roman numerals to determine which charge to use if they can have more than one. So asking this question is actually a question of whether or not we need a Roman numeral. So it goes like this. If the positive ion doesn't have more than one charge, which is a weird way of saying it's only got one charge. So if the positive ion doesn't have more than one possible charge, just name the salt and you're done. It's that simple. Now, what if it does have more than one possible charge? Well, if that's the case, you need to figure out what the Roman numeral is. And the way to do that is through a process called working it backwards. The working it backwards process is a 3-step mathematical process. It involves multiplication, then it involves a process of setting something equal, and then it involves a division. And of course, I'll show you what this means in a minute. Right now, just write it down. So the process once again is this. When we're naming salts, first thing, look up the positive ion. If it can only have one charge, name the salt. If it can have more than one charge, we've got to figure out what that charge is. That will tell us the Roman numeral. And we do that through a process called which is the process of multiplying, setting something equal, and then dividing. So once again in review, I'm afraid my microphone cut out. What we're going to do is we're going to look up the positive ion. Can it only have one charge? Just name the salt. If it can have more than one charge, then we're going to figure out what the charge and therefore the Roman numeral is through this process of working it backwards. So let's look at some examples. So the first salt that we're going to write the name for is FeCl3. So the very first thing that we do is we look up the positive ion. Looking on your periodic table, you'll see that Fe is element 26, and sure enough, it can have more than one charge. It can be +3, +2, or +6. So we need to figure out what that charge is. The way that we do this is through the process of working it backwards. So get this in your notes, and then join me as we do this. Here's how this works. First thing we're going to do is we're going to split the salt in half between the positive and negative. Then at that point, what we do is we find the charge. We start on the right, and we find the charge of the negative ion. And if you look at chlorine, element 17, it has a lot of different charges it can be. But the only negative charge that it can be is -1. And we know that we need the negative charge because it's the second ion, meaning it has to be negative. So once we figured this out, this always flows the same way. This is the work it backwards process. It's a multiply, set it equal, and a divide. So follow along with me. So the first thing we're going to do is multiply. -1 times 3 is -3. Now step 2, set the other side equal. So if the negative charge is -3, the positive charge must then be +3. Now we divide. So we divide by the number of iron atoms that are present, Fe. And you'll notice that there is 1 Fe. There is no subscript. It's understood to be 1. So we divide by 1. And +3 divided by 1 is 3. That means that this iron has a +3 charge, and that's the Roman numeral. So when we write the formula, this would then be iron 3, and then chlorine, just like last time, becomes chloride. So this salt would then be called iron 3 chloride. Notice the 3 does not mean that there are 3 irons. There aren't. There's only 1. The 3 means that that iron ion has a charge of +3. So let's try another one. Looking at this guy, Ni3 PO42. So the first thing we do, please don't forget to do this, the first thing we do is look up nickel, and nickel can either be +2 or +3. It's element 28. It's got more than 1 charge. So what do? Well, we break this thing in half. Then we always start on the right, and we need to know the charge. Now you'll notice that our ion is PO4. So we need the charge of PO4. We find that on the right side of the polyatomic ion chart, and its charge is -3. At this point, we have all the information that we need, and we just need to go multiply, set it equal, divide. So first we're going to multiply. So how many PO4s do we have? Well, we have 2. So each PO4 has a charge of -3, but there's 2 of them. So -3 times 2 is -6. Then we set this equal. So if the negative charge is -6, the positive charge has got to be +6. Then we need to divide. And so the question is, if we have a +6 charge, how many nickel atoms create that +6 charge? And the answer is 3. So 6 divided by 3 means that nickel has a charge of +2. That is then the Roman numeral. So this would be nickel 2, and then PO4 is phosphate. So this salt would be nickel 2 phosphate. Again, notice that doesn't mean there's 2 nickels. It means the charge of each nickel is +2. Moving along. Cu2SO4. First thing we do, you're going to forget. First thing we do, look up the charge of nickel or of copper. And guys, copper can have more than 1 charge. It can be +2 or +1. That means that we've got to split this in half. We've got to break it down. Now guys, this is a little tricky. What we need now is the charge of the negative ion. But notice that the negative ion, and you know what, I'm going to clean up my mess so this stands out a little better. So we're going to break this in half, and then my negative ion is SO4. So we find that on the polyatomic ion chart. It's in the center column, 5 from the bottom. SO4 is sulfate, and its charge is -2. So again, we've got the information that we need to do this. The multiplication, though, is the tricky bit. So we know that SO4 has a charge of -2. But what do we multiply to find the total charge? And interestingly, guys, the answer is not 4. Each SO4 has a charge of -2. But how many SO4s are there? There's only 1. If there was more than that, it would be in parentheses. So we have 1 SO4 with a charge of -2. So this is -2. Then the positive charge has got to be +2. And now we divide. And that +2 charge is created by 2 copper atoms. So 2 divided by 2 is 1. So the charge of that copper atom, each of those copper atoms, is +1. So this salt would be called copper 1 sulfate. So now you're asking yourself, wait a minute, if it's a 1, do I have to put it? And the answer is absolutely. Because if you didn't put the Roman numeral 1, we wouldn't know what charge to use. So you've got to put the 1. Okay, so now guys, let's do one last example, and then we're close to wrapping up for the day, and you'll have the opportunity to work on your homework. So the last one that we're going to do is magnesium nitrate. So magnesium nitrate, we break this in half, and we find nitrate, and nitrate is obviously polyatomic, it's NO3. It's in the left-hand column, over on the left, NO3, and nitrate has a charge of -1. So now we multiply. -1 times 2 is -2, so the positive charge is +2, and that +2 charge is divided by 1 magnesium. So the charge of magnesium is +2, and so we would name this magnesium 2 nitrate. Except for that's completely wrong. And the reason that it's wrong is because we didn't look up magnesium first. Because go to your periodic table and look up magnesium, and magnesium can only have 1 charge. Magnesium can only be +2. So breaking this apart and working it backwards only verified what we already know. We already know magnesium is +2. That's all it can be. And as a result, putting the Roman numeral is wrong, so working it backwards is unnecessary. So starting over, first thing we're going to do is we're going to look up magnesium. And magnesium only has 1 charge. It's +2. And because magnesium can only have 1 charge, we just name this magnesium, and then NO3 is nitrate, and this salt is magnesium nitrate. That's all there is to it. If it can only have 1 charge, name the salt, no Roman numerals. Okay, so there you have it. Today, guys, what we did is we talked about polyatomic ions. We got ourselves familiar with this polyatomic ion chart, and then we figured out how to write the formulas for complex salts, salts that contain polyatomics, and just now we figured out how to write the names from the formulas. There's one more thing that we need to do, though, that is actually a skill that you're going to need to do the lab later on in this unit. And so the last thing that we need to do is talk about a concept called solubility. You may remember that we talked about this in the previous unit. We watched videos that showed how salts dissolve into water. And we touched on the idea of solubility. We understand visually, conceptually, what happens when something dissolves. What we didn't talk about is what things do and don't dissolve in water. We talked a little bit about it because we said polar things do dissolve in water and non-polar things don't. Well, it turns out it's not quite that simple. There are actually some salts that do not dissolve in water. So how do we know? How do we know which salts do and which salts don't dissolve in water? Well, here's the idea. When we talk about solubility, we're talking about a measure of a substance's ability to dissolve in a liquid, typically water. So, a new term that you need to know for the lab, it's the term precipitate. If you have a salt that does not dissolve in water, we give it a different name. We call it a precipitate. So based on these ideas, we can now answer the question. We understand solubility means whether or not it dissolves, and if it doesn't, we call it a precipitate. So let's answer the question. Do these salts dissolve in water? Well, which salts? Well, take, for example, potassium hydroxide. Does potassium hydroxide dissolve in water? How do we know? Well, guys, this is not something that you will have to memorize, frankly, until you come back for AP next year. But what you're going to find out is that it's actually not that much to memorize, because there's a couple quick and easy tricks that will help you figure this out. And we talk about those in AP. So how are you going to know whether or not these things dissolve in water? And the answer is grab your yellow ion chart and flip it over on the back. And you'll notice on the back we have what's called a solubility table. Notice how it's organized. Down the left-hand side, you have all of the positive ions, the metals, and also ammonium, a polyatomic. Then across the top, you've got the negative ions. Some of them are polyatomic, some of them are elemental. This allows you then to look up the solubilities of the salts. Notice across the top, S is soluble, P means slightly soluble. Actually, it's from partly soluble. I means insoluble. D means that it decomposes in water, which is different than dissolving. And then a dash means that the salt doesn't exist. So how do we know if potassium hydroxide dissolves in water? Well, find potassium. It's about 5 from the bottom on the left, and then find hydroxide kind of in the middle on the top and bring those two together. And when you do, you'll notice that you see the letter S where potassium meets hydroxide. So that means that this substance is soluble. So we would put an S, and you'll be doing this in homework. So let's take a look at another one. Well, what about this? What about cobalt chloride? So we find cobalt on the left, and then we find chloride across the top, and we bring cobalt and we bring chloride together, and you'll notice that this one as well, this one as well has an S, indicating that it does dissolve in water. So let's do one more. FeC2O4. Fe is iron. You'll find that on the left. And then C2O4 is oxalate. You'll find that about 6 from the right. And you bring those together, and what do you see? Does this dissolve in water? Tricky, right? What's the answer? Well, guys, the answer depends. The answer depends on what? Well, the answer depends on which charge the iron atom has. Is this iron with a +3 charge, or is this iron with a +2 charge? Well, guys, to find out, guess what we have to do? We have to work it backwards. So we've got FeC2O4. We split this in half. We look up the charge of oxalate, and oxalate is -2. Now, what do we multiply the -2 by? By the 4? We don't. The ion is C2O4. That's what has a -2 charge, and there's only one of them. So -2 times 1 is -2, so this is +2. That +2 charge then is divided by 1 iron. That means that iron is +2. So now we can come over and see that iron is +2, and when we connect that with, where did it go? There's oxalate. When we connect the iron 2 with oxalate, we find that there is a letter I there, meaning that that is insoluble. What you'll see in the lab is that will be a precipitate. So this will actually be your homework for today. Guys, you'll notice that this is a lengthy assignment. You need a lot of practice. This is assignment number 2 in your homework packet. There are about 35 examples of each of these. Do these on another sheet of paper. You try to cram these in small spaces and you're just going to get in trouble. But please notice you're not just writing names and formulas. The left-hand column, you are given the name, you're writing the formula. Right-hand column, you're given the formula, you're writing the name. You're also looking up their solubilities. But guys, what you're going to see is that many of these salts are not on our solubility tables. If that's the case, just write down NG for not given, because those solubilities are not given on our tables. So guys, the rest of the day today is yours to work on your homework. Anything that you don't get done will be homework for the next couple evenings. And when we get back together next time, we're actually going to talk about these similar processes of writing names and formulas, only now we're not going to do it for salts, we're going to be doing it for molecules. Don't think, though, that that means that this is going to just go behind you, because what you're going to find is you're going to be doing these in next time's homework as well. So do make sure that you figure these out. So go ahead and grab your homework, and let's get started.